Hi, everyone, and welcome to another Project Blue Fall live chat presented by AltaSea. We're so happy you could join us. Our guest today is Dr. Yi Chao. He is the founder and CEO of Seatrec. If this is your first time tuning in to one of our events, welcome, and we're glad you could join us. We'll be doing a Q&A conversation following his presentation, so please feel free to ask any questions you might have in the Q&A function or the chat box below. We have one quick announcement before we get this started. AltaSea is hosting their first community open house on campus in over 2 years on the future of ocean robotics. Rusty Jahangir of Blue Robotics and Ann Carpenter of Braid Theory will both be giving presentations. So please come down to AltaSea on Saturday, November 6th at 10 a.m. That's Saturday, November 6th at 10 a.m. Come tour the campus, speak to the people paving the way for the blue economy. We can't wait to see your faces. Now to our guest, Dr. Yi Chao is the founder and CEO of Seatrec. Seatrec was founded to provide clean energy for remote off-grid locations. Dr. Chao spent 2 decades at the NASA Jet Propulsion Laboratory, right in my backyard, before making the jump to Seatrec. Dr. Chao, thanks for joining us. The floor is yours.
Thank you very much. Can you hear me okay? See my slides okay?
I can hear you great and see your slides fine.
Thank you so much. Thank you, Scott. Thanks to AltaSea for providing this opportunity to talk about ocean monitoring. We're getting into a little bit deeper into how do we monitor the ocean in a persistent and a sustainable manner. For this audience, I don't have to spend too much time to see why we have to study the ocean in great details. As you know, ocean play an important role, regulate our weather, our climate, including hurricanes. And not too long ago, if we know more about ocean conditions, we can tell the difference between a Category 3 and Category 4 or even Category 5 hurricane approaching landfall. And ocean ecosystem, we want to protect them in many different ways, and ranging from plastic in the ocean all the way to collect our natural resources from conservation point of view as well. So I will kick off my presentation here, and if I'm able to forward my slides. So I start with assertion: ocean is poorly monitored. As you know, very challenging to put instrument at sea. It's very costly to go out in the ocean, particularly go around away from the coastline. So there are relatively sparse data to be collected in the ocean to help us to make decisions to set up operations in the ocean. So I did a little Google search early this morning, and then if I type my zip code and say what's the temperature in where I am right now in northern San Diego, I get all kind of website tell me about the next 10 days weather forecast, the rainfall, the temperature. But if I try to locate a point in the middle of the ocean, I type in a dateline, the equator, 500 meters, and then they point me a Pacific Wikipedia page. So clearly there's very little information we can get from any sources to know about the 3-dimensional ocean, particularly below the surface where satellite cannot see. So just go a little bit deeper, I can further quantify. We are not really monitoring the ocean at the appropriate spatial and temporal scales and the resolution so that we can help decision makers to make better decisions. So that's where I'm trying to make an effort here to improve ocean monitoring capabilities. And one specific example I can give you, if you go to a Google map or Google Earth and then see the ocean to see where the bathymetry, the map of our seafloors, and then such a fundamental maps you would imagine is make such importance of the scientific research, blue economy, and education, managing our living resources, even geopolitical science. We need to know accurate maps to navigate, to help us to make decisions. And you probably don't want to go out of the door these days without have a smartphone getting a street map before you make the next trip. But if you go to the Google map or Google Earth, you would think ocean seafloor is mapped because you see color everywhere. You see oceans blue, they are deep. But if you take a next level of details, and then say how much ocean is really being mapped in high resolution. And that's what I shown on the right-hand side, is kind of focus on the Pacific Ocean around Hawaii Island. And turned out it's about only 20% of the ocean be ever mapped by in situ sonars. And then the rest of the 80% are really extrapolated from satellite data and then some of the computer models. So that's why people say we know more about the surface of the moon or even surface of Mars than our own seafloor. So 80% of the seafloor, almost twice the size of Mars surface, never been mapped. So that's an important parameter if you want to take home. 20% of the seafloor being mapped, we need to map the 80% gap. It's a huge gap, but if you drill down a little bit near the Hawaii, you will see most of the coastal areas where we live are really good, well mapped. In Hawaii, you can see that area, all the seamount, you know how tall they are, what kind of shape, are they circles and elliptical shapes. This is because of the availability, coastal access, and those are extremely well mapped at a higher resolution. But it doesn't take you too long to go to another coast. This is a coast of South America, of Chile. And then you will see this is a huge amount of gaps in between the ship tracks of the sonars. So basically you only map a certain seamount where have either scientific expedition or some industry demands. So you'll go out, charter a boat and go out to measure them. There are 30,000 seamount total, and then highlighted the black dots there. It's only 20% of those seamount in the white dots ever be mapped, even partially. So we don't really know the rest of the seamount, how tall they are, what kind of shape they are. So you can tell this is it's a huge undertaking. The poor map of the seafloor is mainly because of the access is extremely difficult. Mapping seafloor in the modern technology, take a sonar on the ship, or you recently more and more use of the robotic vehicles to carry those sonars. But in either operation, you need a big ships, go there and burn diesels and then have 10, 20 people on board, work 24/7 to charter those bathymetry map as I illustrate in the left-hand side. And typically ship costs offshore away from the coast cost $50,000 a day. It's a simple math. You can say if I 80% of the seafloor map I need to map, where it takes 300 ship years. If you have 30 ships, take about a decade. You have 3 ships, take 100 years. So if you calculate those costs, is on the order of $5 billion. So no wonder if you take a NASA's budget, you take multi-billion-dollar mission, you map surface of Mars. For our seafloor mapping, clearly this is not the resources available to us anytime soon. So we have to be really innovative and then think about other ideas. How do we map the seafloor and then doing ocean monitoring in a persistent manner? In other words, how do we eliminate or reduce use of ships and then crews on the ship? And then more importantly, how to do in a sustainable way. So we eliminate the fossil fuels and then consumables like batteries used by autonomous robotic systems. And then so start to use the clean renewable energy sources. So this is a really exciting time because we benefit from many other breakthrough advances in the other type of technology space, particularly robotic revolution in the last decade or two. I'm sure you have a smart Roomba at home and then rely on AI and machine learning to do the mapping of the seafloor for your room floor and then clean it up and sending the data to the clouds. And then for ocean, also we are in the crossroad, have increasing availability of the satellite communication, the low cost in the low Earth orbit, in terms of sending the data from the middle of the ocean to the cloud, allow us to manage the data in a cost-effective manner. So we are really in the perfect location and time and space to embark a robotic revolution in ocean exploration and ocean mapping. And just the last week, extremely happy to see our startup company in our space, sail drone in the Bay Area, successfully closed their Series C financing on $100 million. And this is a amount of funding you really heard about in our community, and then really open a new chapter in the robotic ocean exploration, and then leveraging surface solar energy and then the wind energy to propel these sail drones vehicles go around the globe in a persistence manner. This is the beginning of our new chapter of Ocean Robotic Revolution. We need 10 or even 100 more companies like sail drones is to really monitor the ocean in the full three-dimensional manner. The picture on the left show you a couple of cross sections, and you can see ocean is more complex than just the surface layer you can detect from satellites. There's a fairly complex distributions of ocean conditions, depends on the latitudes and then the longitudes, and also the time. The animation on the right, see how continuously ocean is changing. So just like the weather, so you really need the entire community to monitor the three-dimensional ocean constantly with time. So you can send those information into computer models so you can better predict them to make those information available to the decision makers. One of the robotic programs known as Argo is the closest example I can think about as a robotic fleet of robots to monitor three-dimensional ocean. We call autonomous profiling floats. They communicate to satellite every time to the surface. They can dive into 1,000 meters or even 2,000 meters, and then collect the profiles information from surface to 2,000 meters of the ocean conditions, from the physics of the chemistry and the salinity all the way to the chemistry and biology. Is one of the successful programs the community have maturing in the last almost 15 years. After about 2 decades of work, and then there's 4,000 of these float in the ocean today. And as you can see in the left-hand side is one of the most successful international collaboration contributed by 26 different countries. You can see US contribute half of these 4,000 floats, and another tier of the countries and provide a few hundred. And then you have even country provide a few float at a time. So this is an extremely successful collaboration on the international scale. And now you have a framework to monitor the three-dimensional ocean on a continuous basis. The wish list is growing. Recent community meeting, ocean observation night every decade, a couple of years ago, and articulate a grand vision to increase the number of parameters or sensors of these platforms, ranging from go beyond physics to chemistry, the biology. We call the BGC Argo, biogeochemical Argo, to measure the chlorophyll, the oxygen, the nitrate, the pH conditions, and also go deeper from time to time to monitor the ocean warming in response to climate change, and then to think about innovating new sensors to be carried by this kind of successful platforms. So the Argo program really addressed persistence monitoring, had this 24/7, 365. It's really eliminating the use of the ships and the crews, so dramatically reduce the cost of ocean monitoring. Another challenge for this particular program is use those, I call it consumables, and in this case is use limited batteries. This Argo float is basically disposable device because it costs more money to charter boats to recover them. So all of these Argo floats are disposable. They are powered by batteries. The picture on the left show you the life endurance. Typically one float can make about 200 dives. So making dives and from surface to 1,000 meters costs energy, so consume batteries. But once the battery runs out, the float basically cannot surface. They stay at 1,000 meters. So picture on the right, basically show to maintain these 4,000 floats, you have to put in almost 1,000 of these float in the water every year in order to maintain the 4,000 fleet of Argo floats and to replace the dead battery floats. So you can see the green dots basically showing where Argo float reporting data live. And then the right dot show you the dead ones over the last decade. So clearly this is not sustainable if we continue to monitor like this and then increase the capabilities, increase numbers, increasing sensors. Sometimes the sensor is still valuable just because of dead batteries, and then we lost valuable sensors. And then so we lose the opportunity to collect more data. So clearly the solution move forward is look for renewable solutions. This is not my idea. This is the publication proposed by a visionary oceanographer, Henry Stommel, almost 30 years ago when I was in graduate school. And I talk about how the ocean monitoring can leverage the thermal energy in the ocean. Ocean is the biggest reservoir to store heat and then provide by the sun. When you go to the deeper water, getting colder and colder, that's the thermal energy the ocean stores, and that regulate the weather and the climate and hurricanes. So Henry Stommel articulated 30 years ago, this thermal energy can be used to power these autonomous vehicles and sensors to collect important data sets. So that's published in Oceanography in 1989. Talk about how Stommel envisioned this float should be powered by the temperature difference in the ocean, and to deploy up to 1,000 of these. This is the 1 or 2 decades before Argo is remarkably visionary at that time. One of the lead engineers working with Henry Stommel at the Woods Hole Oceanographic Institute in the Cape Cod in Massachusetts, Doug Webb, has been pushing Stommel's ideas and how do we use the thermal energy to power these floats. So Doug even developed a thermal float. So basically he was able to use wax-like materials to change the buoyancy of the float. So essentially use the expansion and contraction of this material going through phase changes and then to drive the buoyancy. And then even Doug deployed a couple of these prototypes. And then eventually battery technology is rapidly growing in the last recent 2 decades. And then eventually the battery powered float getting a lot of commercial attraction, and this thermal float kind of buried on put on the shelf in the library. I was fortunate to have opportunity to work with Doug Webb recently towards the end of my JPL career. And that's where I started about 10 years ago when I worked at NASA Jet Propulsion Lab, is to really look into this Stommel's vision. How do we harvest energy from temperature difference, go beyond Doug Webb's implementation, not only use the phase changing material to changing the volume of the device and drive the buoyancy of the float, but also transition into power generation. So our concept is going 1 step beyond Doug Webb's implementation, is to use the phase change material to go through a solid to liquid phase transition. Every time a float moving up and down, experience a cold temperature and a warm in the deep ocean, a warm temperature at the surface. So essentially, as the float comes to the surface, we melt the material from solid to liquid, and that's generate a volume expansion, and that's mechanical energy will be harvested into electricity through motors and then generators. So the patent was granted to Caltech, and we built with the funding from the Office of Naval Research in collaboration with Professor Ross Davis at the Scripps Institute Oceanography, a pioneer in developing profiling floats. So Ross was able to build one of the customized float for us. The JPL team developed the power generation systems. We were able to deploy this thermal powered float into the ocean. And then it's the first self-powered profiling float in the ocean, survived 18 months in the ocean, collecting more than 1,000 dives, profiles, and And then the picture on the right-hand side basically showed both the scientific result on the bottom showing where we deploy. You have a nice temperature difference between surface and 500 meters. It's almost 15, 20 degree temperature difference. So we were able to convert this electricity showing in the upper panel. So every time we melt the material, we spin the turbine, we can generate electricity. When the turbine is spinning, we can output almost 200, 300 watts of power. That's being stored and basically recharge the battery up. So the float consume energy as they profiles, and then we generate energy from the natural environments. If we generate more than the float consumes, essentially we have a persistent float. So the float can last continuously to collect data. So one of the scientific results showing here is in our first part of the mission, we profiled the ocean every 8 hours, 3 profiles a day, just like the weather balloons to monitor the weather change. So capture a lot of the high frequency, fast changing processes. The color bar show the salinity of the ocean. So periodically you have a rainfall, you create this freshwater salinity signal in the upper ocean. In the last half of the mission, we switched back to 10 days and try to mimic the Argo mission, try to conserve the battery power to make a long-lasting floats. So then you can see having a bit additional energy allow you to fast profiles in the ocean can generate a lot of valuable information you are not able to get otherwise. So that's really kind of the quick summary. How do we get this profiling float? Not only we can monitor the ocean in the persistent way with the robotic systems, but also we are able to use the renewable energy to continue to operate in a persistent manner. So this is exactly what Henry Stallman articulated 30 years ago. So now we have developed a technology, platforms. So go back to the typical technology evolution. Essentially, we go from 0 to 1. We build the first prototype. We demonstrate is capable to use the ocean thermal energy to generate electricity, to power the sensors, to deliver the data to the scientists. Now, I think the next step, this is back almost 10 years ago, is how do you go from 1 to 1,000? So in other words, how do you transition a scientific research result to a commercial product so that we can get this technology to everybody who need them so they can go out to collect the data in the persistent and a sustainable manner. So this is the kind of the crossroad, my personal career. I've been evaluating licensing to different companies, and turned out going from 0 to 1 is easy, but a 1 to 1,000 probably is what they call the valley of death. Is required not only the technical breakthroughs, also require market opportunities, implementation risk, and marketing and sales and so forth. So it's a well-known valley of death. And so at that time, it's really it's critical for me to think about a way to accelerate this transition to cross the valley of death. So I decided to take a chance, read some books, and then to start the commercialization process. So over the last 5-6 years or so, extremely exciting journey. I can talk about this offline or give another presentation if you're interested, to talk about how to transition from academic research to a commercial product. Is take the whole village to support us up to where we are today. And we continue to receive the funding from the government through small business grants, visionary family foundations, the Breakout Lab operated under Teal Foundation, and also the Schmidt Family Foundation, Schmidt Marine Technology Partners, really instrumental getting some early grants into the startup company, and continue to get government support. And then a lot of private investors step up to help us to develop the commercial product, which is a government contract was not able to do. and continue to raise our funds to getting new IP, new patents, and then to work with industries and then eventually grow to a commercial product. So time forwards a few years now, we have a commercial product we are ready to deliver to any customers in the globe. Essentially, the thermal powered profiling float, so we can attach a one modular system or a two modular system, depends on the sensor being attached, the energy required. So essentially you can profile as frequent as you want and have essentially unlimited endurance as long your sensor is working. And also you can think about additional sensors. So now we can scale up our energy production to support to power more sensors, which is not beyond traditional oceanography of my career. So I will try to highlight a few applications as we move on the next few slides. We also developed a simulation tool for our customers to try to explore our technology. 2/3 of the global ocean have the thermal temperature difference. Though in those areas, you will be able to recharge the battery by the ocean as you continue to carry out your mission. So this is a particular simulator. You can release your float in computer. So we call the digital twin or float trajectory simulator. Basically, you can release a float with traditional batteries and also with our energy power system. So assumption, this case study, I show you, we assume we go down to 1,000 meters and then we do a daily profile. So every 24 hours, we do go to 1,000 meter depth, come back to this, send the data through the satellite, and then to continue. And then the battery capacity on the left-hand side, we assume can make 360 dives. It's just for simplicity, making a year lifetime. After you profile a year, basically you consume all your batteries. So the result here is highlighted because we released in Hawaii, a nice place to find a nitro temperature difference. Essentially the trajectory over the red and show you the battery powered float. So basically after 365, after 1 year or so, so essentially we consume all the electricity on the board, and that float is claimed being lost, right? And then our thermal powered float continue to profiles, as you see in the bars after 3 years, because of the subtropical environments. Every time we recharge the battery more than what you consume. So essentially after you operate 3 years, this float is still fully charged. So essentially this float can continue to go on for number of many additional years. I had to stop the simulation because I doing this calculation on Amazon cloud, and every year I calculate and charge me computer time on the cloud. So basically I stopped after 3 years to demonstrate you can continue to profiles in almost indefinitely. Going back to the application I started earlier on the seafloor mapping. So now we have a very mature and capable platforms. And then how do we apply this to map the seafloors, which I articulated at the beginning of the presentation. So this is the proposal we are working with Professor Larry Mayer and the University of New Hampshire. It's recently been funded by the Schmidt Family Foundation through the Schmidt Marine Technology Partners. So essentially we are combining 3 mature technology components into a single system. So we're leveraging Argo type of profiling float that have been used for almost 20 years, and then introduce our thermal energy harvesting system, and then work with commercial Echosounders. It's a single beam, active acoustic Echosounder. So essentially you'll send the signal at 1,000 meters to the seafloor and then measure the travel time so you can re-infer the bathymetry below. So you can get a fairly high resolution on the order of 100 meter reading of the seafloor map, and essentially go back the 80% gap, for example. So all this black dot at the seamount never been mapped. All the gray area are the gaps between those ship track sonars. So we see this as one of the cost-effective technology to map this 80% gap. So we hope to contribute to the international effort called the Seabed 2030 as part of the United Nations Decade of the Ocean programs to map this 80% of the gap and the 30,000 seamount. So essentially we can think about release one float on each of the black dots to map the 30,000 of them. And then within a year, we probably can map each one of the seamount, 30,000 of them on the globe. So that's the ambitious project. So currently we have a pilot program funded by the Schmidt Family Foundation, hopefully to validate this technology and then to deliver the data as high quality as the ship sonar measurement, the autonomous underwater vehicles, and also many of the autonomous surface vessels like sail drones, and I mentioned earlier on. Another possible ideas is to attach hydrophones into this type of new platforms. As you know, it's important to understand the sound in the ocean, not only to quantify the noise coming from both natural and man-made sources, but as well as from conservation point of view to do a marine mammal detections and try to protect them, provide those information to shipping companies, for example, and then also use acoustic as a source to locate object in the ocean underwater. Traditionally, you cannot do with the GPS in the air or on the surface. So that's another direction we are pursuing. We are collaborating with acoustic expert and then John Joseph from Naval Postgraduate School and John Ryan from Monterey Bay Aquarium Research Institute have traditionally hydrophones and then installed on the seafloor. And then most of these hydrophones at about 1,000 meters, 500 meters of range, primarily powered by cables near the coast, because you need to do a continuous monitoring. And then we envision our autonomous system is one way to provide almost a drifting hydrophones, allow us to not only deploy in the coastal ocean, but also in the middle of the ocean to help us to quantify the sound distribution and the sources as well. I was in a major ocean conference last week, Ocean Business in Southampton, the UK. There's a tremendous about new sensors available to monitor the ocean, ranging from the lab on the chip to measure all different kind of chemistry in the ocean, all the way to environmental DNAs, and also emerging currently used effectively by autonomous underwater vehicles and on the ships, and all the way to measure the microplastic in the ocean. So we see ourselves provide platforms and profiling platform in the persistent and the sustainable manner. And essentially we have infinite energy, infinite thermal energy sources, and then the potential is tremendous to bring additional sensors to this platform and to measure the data everywhere and all the time. So this is a perfect time to kick off ocean monitoring technology like this. This is the decades of the ocean development and sustainability declared by United Nations. We are kicking off 2021 as the first year of the decades. And hopefully by the end of the decade, 2030, when I go to Google again, if I type ocean parameter, nitrate, pH, or temperature, salinity, 1,000 meters, and latitude, longitude, hopefully Google will point me to the right source of the data rather than some question mark right now is you cannot get anywhere. So I will wrap up here with my presentation here. I have my contact information. I'll be happy to get the Q&A and going, and then feel free to reach out to me if not able to answer your question directly afterwards. Thank you very much.
Thank you so much, Dr. Chao. This was very insightful. To kick it off, I kind of wanted to touch on the importance of mapping the seafloor. You talked about it at the beginning, for those who might have joined late, the Seabed 2030 campaign to map the entire seafloor. Why is this so important to get this done?
Yeah, you can think about that question in many different dimensions. It's a fundamental map of the ocean. So you probably wouldn't drive out these days without a map on the smartphone. So that's probably a layperson's response. You'll need a map to navigate. Of course, you'll need map to explore the ocean. You know where the seamounts are. You need to know the circulation, the physical conditions, and the ecosystem. Most of the time near those seamount, near those changes of the bathymetry, there are very interesting processes, physical processes, and the ecosystem associated with those. So you wanna know those information before you can protect them. So establish marine protected areas, or even setting regulations in the open ocean before we can start mining rare metals in the ocean, for example. If you want to put a wind farm on the West Coast, you certainly want to know the bathymetry, the environmental conditions, and then you want to monitor the ocean health and how you impact the environment with our wind farm offshore. I think wind farm is coming, whether you like it or not, in the West Coast. So we need to figure out a way to provide the information to not only provide to the wind farm operators, but also provide the information to regulatory agencies and conservation groups, and then try to arm the information, provide the information so they can make better decisions.
So a couple things that have happened in our oceans lately, right off the coast, the oil spill about this month, the discovery of all the DDT in the ocean, those kind of things. Would this help avoid those or mitigate the effects of this?
Well, our technology is primarily targeting offshore applications. Those are remote areas. Is like our company statement is we provide energy in the remote, difficult to reach areas. In the coastal areas is reachable by ships, and then we can refuel easily. Sometimes you can have cables, and then you can have power that way. So you're less reliant on renewable energy in the ocean, in the coastal zone. So mostly the urgent need for our technology, those areas is expensive to access by ships, and then it's almost impossible to lay fiber optic cables to provide power or data transfer. So the autonomous system powered by our system is a very unique alternative.
So you said hard to reach places, very remote. So that kind of brings me to my next question. So a stat that always boggles my mind is how the ocean is makes up 70% of the Earth, and almost 80% remains unexplored. So it kind of seems like a daunting task to map the entire seabed by 2030. Do you think this timeline is possible to hit, especially with your technology?
I'm optimistic, and then I think the communities step up to the challenge. And as I mentioned, I'm extremely happy for Saildrone, and then raise $100 million for surface autonomous system to map the seafloor. They built 70-foot long vessel, primarily focused on seafloor mapping. We are gearing up with our system to map the seafloor from 1,000 meters down, so we don't have to have a big system, so we save power, and then so we can essentially deliver the same information. And I would imagine this decade we take 10, 100 companies like Saildrone to step up to meet the challenge of Seabed 2030, and then many other environmental programs, and then to monitor not only the seabed, the seafloor, but also we want to monitor the ocean conditions as well.
So ambitious, but you're hopeful, essentially.
I'm extremely optimistic, and the community is up to the challenge. I think, as I mentioned earlier, we are in the technology breakthrough in many different disciplines. We have benefit from cloud computing, which is not available a decade ago, robotic revolution, AI and machine learning. now we can much smarter way to optimize our robotic system in the ocean. If the Roomba can, can remember the floor of your room, then we can do smart mapping in the ocean as well. So we save resources and maximize the data return.
So this question will probably make more sense to you than it makes to me. George asks, Yi, do you use on a moored profiling CTD with minimum depth, minimum delta T needed?
Yeah, we are talk about we can apply to moored systems. Doesn't have to be autonomous, untethered. We typically looking for 5 to 10 degrees Celsius difference between the surface and the parking depth, and then I have to cross the phase change temperature in order for us to generate electricity. So in other words, if we set 10 degrees C at the phase change temperature, assuming that's 300 meters, you have to cross them all the time. Every time you cross, we harvest energy, and then we basically recharge your battery. So the more you can cross them, the more electricity you have, and then you return more data.
Okay, so kind of zooming out a little bit, you said when you were talking about the possibility of this happening, you said the community will step up. So a lot of the people that are watching are students, general public, maybe they're in PhD programs. What do you mean by step? What can the average citizen, everyday citizen, do to help this cause?
Well, the plastic is a good example. I think everybody can do their part. Awareness in the last few years on the plastic in the ocean is remarkable, right? So we bring our own bag to go shopping, right, in the grocery store. And then we get a paper straws, and then we start using metal straws. So we reuse them. So we stop using a lot of these plastic. That's one good example, from all ages, every sector can help save the ocean. So you can pick any of the problems we are facing: renewable energy, offshore, climate change, seafloor mapping, ecosystem health, offshore farming. So you can pick any one of these disciplines, and then you can step up and then contribute. And you need not only oceanographers, you need a physicist, chemist, biologist, computer scientist, AI expert, machine learning, pilot of the robots, all of the above, cloud computing expert, Python programmers, you name it, right? And then business school, physical sciences, we need 100 sail drone companies. You need a lot of MBAs to step up to contribute to the blue economy, and which is something, as a oceanographer, we don't know how, we don't have the right training. So have more people involved working with the community, and then really build this blue economy, which is emerging.
Okay, so zooming out to you in your career path, can you give us like an overview how you got started, what drew you to this field? Were you always, as a kid, did you know this was going to be something 40 years down the line you'd be going into?
No, I was trained as oceanographer. I spent more than 20 years working as a scientist for NASA. I launched a salinity satellite to measure salinity from space from the first time. Working with colleagues to operate those robots. So throughout the process, I realized this energy problem. So kind of running into this Henry Stolmo's paper almost by accident. It's published in 1989. I didn't read it until probably 20 years ago later. So probably 15 years ago, I start running into this paper, and then start to dig in to reach out to the colleague, Doug Webb, he's an engineer, and he's still active working on web research, already acquired by Teledyne Technologies, but he still show up to work every day in the 80s. So I have an opportunity to talk to those visionary pioneers in the past, Professor Russ Davis at Scripps, developing the float from day one. So really benefit that knowledge, and then try to bring in our contribution and to put together engineering team to solve this technical problem from 0 to 1. And then I really hate to see the technology, the patent being put on the shelf on the wall, and then without being applied, and then waiting for another 2 decades. And I don't have a lot of time to waste to wait for this technology automatically being picked up. So the only way to speed up is for me to proceed and then commercialize them.
So we talked about it right before we went live, but can you touch on how you made that jump from an academic background to the commercialization effort? What's been, you know, your biggest challenges? What's been something that's inspired you during this jump?
Yeah, I think being a scientist, I think one thing we learned as a scientist goes through the Ph.D. program is solve problems, right? So most of the time we solve technical problems, and then certainly a lot of the challenges I didn't anticipate is as challenging as running a business. I read a couple books before I quit my job. I thought, how hard it can be just, run spreadsheet and then go to raise money, right? So I certainly, there's a certain time you underestimate the challenges, but it still is really enjoy the process to learn new things every day. As a researcher now, I just learn different things in different disciplines. So really enjoyable journey, and I hope to contribute to many of these seabed 2030, Argo, and climate change and energy. So just the time is so important, and I just cannot sit there and wait another decades and then things happen automatically.
So you mentioned waiting another decade. What's next for Seatrec? What's the next step? What does the next decade look for you guys?
We have a very exciting decade coming up. Is really scale up this technology. The platform is really maturing. We are looking at apply this platform to many different disciplines like seabed mapping, environmental monitoring, and sound detection in the ocean. So many different disciplines we want to break into. So for us, it's really partner with many of the sensor companies to find the challenging problem, is to contribute and then be part of the community.
And so to get this done and to really help mitigate climate change, what's next for the industry at large? You mentioned that other company that raised $100 million. You said you needed 100 more of those companies to get this done.
Yeah,
what's next?
Like a biotech, right? So
yeah.
You need, you read any book of starting a company, 10 company, 1 out of 10 are survive after 3 years, and then out of this one survive is only a few percent being successful, right? So I think we need many companies like Sail Drones to working towards the common goal, and then if there's 1% of those companies, and then eventually end up what they call the unicorn status, and then to make a difference in the blue economy and energy and climate. And that's what we need. We just need more numbers. So if we have only 10 companies, we may not have a unicorn to make a meaningful contribution. But if we have 100 companies, guarantee we have one or few companies will be successful. So if you play the numbers game, we just need more people involved, more company, more people take a risk, more people supporting, investing, and partnering, and to be part of the process.
Yeah. So we have a late question coming in from Lisa about all of this. She asks, does this effort harm whales or dolphins, and I guess sea life at large, with the sonar? And do we know this for sure?
Well, part of the process is try to understand and just to minimize, to have a better information to protect them. So the more information you gather, the better you understand understand how they communicate, how they migrate, and then so that you can help the policymakers and to make better policies to protect them. So if you don't have the information, you probably will regret something you didn't think about. But the more information you have, the better policy, better decision you will make. And then the community is very careful to deploy things in the ocean, more sustainable way. And then obviously in the earlier phase, we put in a lot of things in the ocean, but I think the community should learn from the past lessons to be more sustainable as we move forward, so we don't really create problems. So that's really our philosophy. I think community is working towards in a more sustainable way to monitor the ocean, to protect the ocean.
Got it. So like I mentioned earlier, we got a lot of students on here that this might have sparked an interest for them. What do you recommend they do to, work in this field, to be an innovator like you? Any advice?
Well, the problem become very interdisciplinary. So I guess my advice to learn as much as you can and take as many courses as you possibly can. You'll never know which class will benefit your career down the road. Sometime I regret to take, missing those classes because I thought a waste of time, because as an oceanographer, why I need to take certain classes, right? So you'll never know. Time change. You don't have a 30, 40 years career with single discipline. So now you have to know how to pivot, how to make the change. So be versatile, be broad. The school is a good opportunity to learn as broad as possible, to prepare yourself as much as you can, and then to address those uncertainties down the road.
Awesome. Well, I think we don't have any more questions coming in, so I give you the floor for any final thoughts you have. Anything you want to share?
Yeah, thank you for the opportunity. And L2C, I've been watching the growth of L2C. Extremely excited to see it's come along, and facilities and all the companies, and then center around L2C. It will be a great addition to the ecosystem. Looking forward to more interaction with L2C and more programs like this, and then robotic events you were talking about earlier. I think we need more ecosystem coordinated to build the community, and then to develop 100 sail drone companies down there in the next decades.
Great. Well, again, thank you so much for joining us. This has been awesome. And to plug it one last time, because it ties in very well about the future of ocean robotics, All2Sea, that's the whole community open house on Saturday, November 6th, is all about the future of ocean robotics. We got Rusty Jahangir of Blue Robotics and Ann Carpenter of Braid Theater. They'll both be giving presentations. So again, everyone, please come down to All2Sea Saturday, November 6th at 10 a.m. And you can tour the campus, speak to the people that are leading the way, like Dr. Chao. Again, Dr. Chao, can't thank you enough for joining us. And I hope you have a great weekend.
Thank you very much. Looking forward to it.